Hello, everyone. Welcome back to our probability. And today we're going to talk about and problems or problems at least once and the conditional. So we have a few topics we're going to be talking about. Let's start off with the difference between a dependent and an independent event. And I will be honest here that it might make more sense when we get into a problem. So I can kind of explain the difference between an independent and a dependent with an actual problem. But basically, two events are considered independent if the occurrence of one event does not affect the probability of the other event. If that is the case, and that's why we have to talk about independent versus dependent, because with the and probability questions, there is a difference with the formula. If they are independent, so one probability is not affected by the other, then the probability of A and B is just the probability of A times the probability of B. And this would continue no matter how many events you have. You can see it would just keep going. Now, if the events are dependent, okay, that means that the probability of one event is going to affect the probability of the other event. And like I said, I'm going to do a couple of examples so you can see which one would be independent and which one would be dependent. So that one would be a little different because what we're going to look at then is the probability of A and B. You would have the probability of A times the probability of B given A occurred. That's what that means. So the probability of B given A means that A happened. Okay, so let's do a couple of examples. I think it's just going to make more sense when we just dive right into one to talk about the difference between independent and dependent. Example 1. 2 cards are drawn with replacement. Okay, so this means when I draw these 2 cards, I'm going to draw one, but then put it right back into the deck and then draw a second card. Find the probability that the first card is a queen and the second is a face card. Now, when I do these, I like to just, you're going to see how I make my probability. So I try to make it kind of short but simple, but yet to the point. All right, so we want the probability that the first card is a queen. Okay, and I'm just going to use Q. And the second card is a face card. All right, so we want the probability that when I draw these 2 cards, the first card is a queen and the second is a face card. Now, when this is asking us, let's first decide, is this independent or dependent events? Well, right here, the key word is right here. It's with replacement. That means after I draw the first card, I'm going to put it back. So I still have 52 cards when I draw the second card. These are considered then independent events, because it doesn't matter what the first card is that I draw. I'm putting it back. And so I'm kind of resetting the probability then back to start. So because they're independent, then what I'm going to do is I'm going to find the probability of a queen times the probability of getting a face card. All right, now we know we have a total of 52 cards. So no matter what, when I multiply, my denominator is going to be 52. But let's go back to that document we looked at in the previous section on the cards. Face cards. So up here, face cards are Jack, Queen, King, right? So there's 4 of each of those, which means we have 4 of each means, oops, let's see if I can get that, which means we have 12 face cards. Okay, so let me go back there. I just realized I kind of worked the second one first, but that's fine. All right, so we have 12 face cards in total. 4 jacks, 4 queens, 4 kings. How many queens do we have? Well, we just said that there are 4 of each of the face cards, so we have 4 queens. And you can see them right here in your document. So that means I have 4. And then remember, when you are multiplying fractions, you just multiply the numerators and then you multiply the denominators. And so if you multiply that out, that's going to give us 48 out of 2,704. Now, you could reduce this. Now I will say there are calculators and probably some computer programs. I know the TI-84, the graphing calculators will reduce these for you, but just to kind of go over that, let me just change the colors real quick. 16 goes into both of these. So you can divide both of those by 16. And what we have would be 3 out of 169. So that would be our answer if we're keeping it in fraction form. Second one, find the probability of obtaining a black card on the first draw and a spade on the second one. So I want the probability of a black card on the first and a spade on the second one. Okay, again, this is still the one with replacement. So these are independent events because we're putting, oops, sorry. See, this is why I cannot write and talk at the same time. Here we go. That would be times. All right, again, out of 52 cards because both of those, we're putting them back in. How many black cards do we have? Let's go back into that picture. And notice right here we wrote down there are 26 cards that are black. So we're going to put 26. How many are spades? All right, a spade is a suit. Okay, that's what we call the suit, spades. And there are, what did we say? 13, right, of every suit. Okay, so there would be 13 spades. Let me go back into here. So let's write that down. Now, I'm going to do this a different way. In the previous problem, notice I multiplied first, then I reduced, which is fine. That's one way to do it. I want to show you another option, and it might be easier because you're not dealing with such large numbers to reduce. I would reduce each of these fractions. For example, 26 and 52. 26 is half of 52. So I know that I could divide both of these numbers by 26. And so reducing that would give me 1/2. Then I'll do the 13 and the 52. Well, 13 goes into 52. So I'm going to divide both of these by 13. And then that's going to give me 1/4. Notice now, this is ready. This is 1/8, and I don't have to worry about reducing the larger fraction. It's up to you how you prefer to reduce your fractions, but those are two options, two different options. All right. Now, we're going to change it up a little bit. Suppose two cards are drawn without replacement. What this means is after I draw the first card, I'm not putting it back. So I have one card missing from the deck when I do the second probability, the second draw as well. So let's talk about that. That means these are dependent events. They're dependent because in this case, my probability of the second card being drawn is affected by the first probability because I'm not putting the card back. So let me show you an example what that would look like. Find the probability of selecting two aces. So I want an ace and an ace. That would be the probability of an ace. Yes, we're still doing that times the probability of an ace. But this one is different because, let me just show you. First one, fine. First one, we want to draw an ace. How many aces are there? Going back to our document, there are 4 aces, one of each suit. Okay, so going back here, there are 4 aces out of 52 cards. Now I'm not putting this over 52. Remember, this says it's without replacement. I'm not putting that card back. So let's say I drew an ace in the first draw, right? Because that's what we're looking at. What is the probability of that happening? It's 4 out of 52. But now I didn't put the card back. So now I have 51 cards. That's what changes. But also something else. We're going to assume that we did get an ace because we're looking at what is the probability of getting 2 aces. So if this one was an ace, How many do I have left now? Because I didn't put it back. I have three aces because we're assuming the first one is an ace because we want to know the probability. All right, so again, we're going to go ahead and again, you can reduce this. It's all up to you on how you do it. Sometimes I reduce at the end. Sometimes I prefer to do it in the beginning. I can't reduce the, let's reduce the 4 out of 52. Now 4 goes into both of those, okay? So we're going to go ahead and reduce that, and that gives me 1 out of 13. And then I'm going to reduce the second fraction. Now for me, I just find it easier to reduce the smaller fractions. I know 3 goes into 51, and here's a little trick of how I know that. If you want to know if 3 goes into any number, you add up the 2 digits. So with 51, I would add up 5 plus 1. 5 plus 1 is 6. I know 3 goes into 6. That means 3 goes into 51. So just a little trick with the 3s. So I know 3 is going to go into that because it will go into the digits when I add them. All right, so I'm going to divide by 3 for both of these. And that's going to give me 1 out of 17. Now I will multiply these, and I will just take the 13 times the 17, and that's going to give me, let's see, my calculator says 221. Just in case, because every problem is different, everything. Sometimes you're asked for the fraction, sometimes you're asked for the decimal. So let's go ahead and take 1 divided by 221, and let's round 3 places. And if you look at your calculator, you should be seeing 0.005 if I round 3 places. That is the probability of getting 2 aces out of 4 when you're looking at a deck of 52 cards. So a very low probability. Let's try B. Find the probability of getting a heart and a spade. Okay, we know that's the probability of a heart times the probability of a spade. How many hearts? Again, that's a suit. Going back to here, here's your hearts, and there's 13, remember, of every suit. So I have 13 hearts out of 52. And how many spades? Well, a spade is another suit. Again, there's 13 of everything. So I have 13 spades because the first was heart. So we didn't lose any spades, but what did we lose? We lost a card. We're not putting it back from the first draw. This is going to be then out of the 51. Now with this one, I'm just going to multiply this through because I'm going to turn this into a decimal. This will give me 169 divided by 2,652. Divide those two numbers and round 3 places, and your probability is 0.064. Now, number 3. We want the probability of rolling 2 6s, so this is on a die, followed by 1 2 on 3 tosses of a fair die. So remember we talked about the die. You have a possible, there are 6 sides to a die. Each one is numbered either 1, 2, up to 6. So here, we want the probability of a 6 and a 6 and a 2. Now we're just rolling a die. This then would be independent events. It's not like a card where we might put it back. We're just rolling, taking 3 tosses on a die, and that's going to tell us how our probability is going to be. So let me just write this out. Then remember, we're just going to multiply every probability. What is the probability of getting any number on a die? Just 1 out of 6, right? So the probability of a 6 would be 1 out of 6. And again, probability of getting a 6 again would be 1 out of 6. What's the probability that now when you roll the die, it's getting a 2? Again, there's only 1 2 on the die out of 6. All of these have the same probability. But all together, when you multiply that out, you get 1 out of 216. That is your probability. Turn that into a decimal, and it's 0.005. Oh, so that looks familiar. So the probability of rolling 2 6s and a 2 is the same probability as up here as getting two aces, drawing two aces in a deck when you are not putting the cards back. Without replacement, we call it. All right, let's go to OR probability. With the OR probability, now this is different. So we just did AND, but now we're going to look at OR. Now we have to look at two things. So with the AND, we were looking at independent and dependent events. Here, we're going to look at non-overlapping versus overlapping. So just to kind of explain this a little bit, when we're talking about OR problems with non-overlapping, it means they can occur together, right? And they are non-overlapping events, meaning neither of those events can happen at the same time. If that's the case, you add the probability. So instead of multiplying, we're now going to add. If they are overlapping events, which means they could occur at the same time, then I'm going to take the probability of A plus the probability of B minus the probability of A and B. Again, just to kind of help you understand a little more of what we mean by overlapping and non-overlapping, let's do a couple of examples so that you can understand a little better with that. All right, we're drawing either a red or a black king with one draw from the deck of cards. So in other words, we're not drawing two cards anymore like we were doing in the previous one. We're drawing one card, and we just want to know what's the probability that when I draw that one card, it's going to be a red 7. You'll notice how I like to write very shortly, or a black king. So that's the same card, but we just want the probability of it being one of those. All right, here's what we mean by non-overlapping and overlapping. Could you have a card, one card, that is a red 7 and a black king at the same time? No, no card exists. So this particular problem, and I'll just put it kind of over here, this is what we would call non-overlapping. And again, it's because a king and a 7 cannot occur at the same time. There's no card with both of those on at the same time. That means that we're just going to take the probability of a red 7 plus the probability of a black king. How many 7s are there? Remember, there's 4 of everything. So we want how many red 7s? Remember, there's 4 of everything, but for reds, there would only be 2 because 2 7s would be red and 2 would be black. And same with the kings. There's 2 black kings and 2 red kings. So that's going to be 2 out of 52. Well, that gives me, and remember, when you are adding fractions, you just keep that common denominator. We don't add those. So that just stays the 52, and we add the numerators. Now, we know we've already done one of these. 4 does go into 52, so I would just divide both of those by 4, and we get 1 out of 13. All right, look at number 2. We want the probability of getting a sum of either a 6, 7, or 8 on a roll of 2 dice. What do we mean by a sum? So let's go back to here, and I have it on here. If you are rolling 2 die, what this graph shows you is what your possibilities could be. The 1, 1 means that the first die rolled a 1 and the second die rolled a 1. Let me jump down over here, right here where you see my mouse. This says that the first die rolled gave you a 4, the second die rolled gave you a 2. So these are the possible combinations you could get from rolling 2 dice. The sum is what you would add inside. So for example, the sum here would be 2, right? If I jump back down to here, the sum here would be 6. And that's what we're looking at. So going back here, we're saying what is the probability, or sorry, yes, of getting either a 6, 7, or 8. This would also be non-overlapping because you cannot have a sum, right? You can't have 2 numbers that add up to 6, but then they also could add up to 7 or 8. Not. This is non-overlapping. Remember, overlapping means that something could occur at the same time. Then that means I want the probability of a 6 plus the probability of 7 plus the probability of an 8. All right, let's go back to this diagram. What we want to see is how many of these. So by the way, there's 36 of these in total. That means, I'm going to go back to here. When we do our probability, each one of these is out of 36 possible combinations. How many of these combinations add up to 6? Here's a nice thing about this chart. Find the first one right here. If you can see my mouse, the 5 and the 1, that adds up to 6. Sums go in diagonals. So notice here, it just goes in a diagonal. So that means I have 1, 2, 3, 4, 5 numbers that add up to a 6. So over here, we would put 5 out of 36. Now, how many add up to a 7? Going back here, I find the 7, which is down here at the bottom. Notice the first one right there. And count diagonal. All of those add up to 7. 1, 2, 3, 4, 5, 6 of them. And then we go back to how many add up to an 8. So I look back over here. That starts here at the bottom, the 6 and the 2. 1, 2, 3, 4, 5 add up to 8. Okay, so 5. Remember, we don't do anything with the denominator, so we're just adding those up. That gives us 16 out of 36. And we know we can divide both of those by 4, and that's going to give us 4 out of 9. All right, let's try another one. What is the probability that you get a heart or a jack? Now this, again, we have to first decide if they're overlapping or non-overlapping. And again, what we're asking is there a card that when I draw it, it could be a heart and a jack at the same time? Let's go back up here. Yeah, it's called the Jack of Hearts. It's a jack and it's a heart at the exact same time. That is what an overlapping event would be. Okay, so this is overlapping. Okay, and that's because the jack and hearts, right? The jack and hearts is an actual card that can happen at the same time. So let me go back into here, because now that just changed how I'm doing this. I'm going to take the probability of a heart plus the probability of a jack minus the probability of a heart and a jack. That's when the formula changes, when you could have this happening at the same time. All right, the probability of a heart. Remember, there are 13 hearts, 13 of every suit. 4 jacks minus how many of those cards is a heart and a jack? Well, it's just the one card, the Jack of Hearts. One card. Now, why do I do this? Why do we do this? Look in here. 13 hearts. One of those is the Jack of Hearts. 4 jacks. One of those is the Jack of Hearts. You have it down here twice because of those two probabilities. That's why we subtract it, so that we're not counting it more than once. All right, add 13 plus 4. That gives you 17 minus 1. That would be 16 out of 52 cards. All right, and again, you can reduce that by 4. And so that gives us 4 out of 13. Okay. Let's do one more. I have 2 on here, but for time, let's just do one more. We're done. We're rolling a die. We want the probability of a number greater than 3. So I'm going to change that to that, or less than 5. Okay. Just as I'm going to write down your number. So remember, on a die, these are your possible numbers. We need to decide if there's any overlapping event. That means, is there a number on the die here that is greater than 3, but also, so you change the or to an and to answer this question if it's overlapping or non-overlapping. Is there a number that is greater than 3 or less than 5, right? So greater than 3 and less than 5 at the same time. What number on the die is greater than 3, but also less than 5? The number 4, right? The number 4. So this is overlapping. And that's because the number of 4 is greater than 3, but also less than 5 at the same time, which means now I'm going to find the probability of, I'm going to jump down here just for room, of each of these, and then subtract anything that would be greater than 3 and less than 5. So how many numbers are greater than 3 on the die? Look back over here, 4, 5, and 6. 3 out of 6. How many numbers are less than 5? Well, looking over here, that would be 1, 2, 3, and 4, right? So 4 numbers out of 6 minus, don't forget, we said that there's one number that's both of these. It's greater than 3 and less than 5, one number. All right, so 3 plus 4 is 7. 7 minus 1 is 6. Look at that. 1 or 100%, meaning you have a 100% probability that when you roll a die, the number is going to be either greater than 3 or less than 5. All right, I'm going to end this video here, and then we're going to go to part 2 of this section.